Yeah, hi. Good evening, everyone, and welcome to problem solving session for week number 9. In this week, I presume you went through magnetics design for power converters. That is magnetics design as an inductor design and the transformer design. So, we will be going through a number of problems. So, today I have tried to increase the number of problems that we hope my screen is visible. So, can you please confirm if my screen is visible?
Yes, sir.
Okay, so yeah. So as I was saying, in this week, you have gone through the magnetics design for power converters. So we will be seeing problems on that. And in order to maximize the number of problems in this concept, so I have the solutions on the slide. So you can just see one by one, okay? And of course, if you have any doubts, you may interject me in the middle or write in the chat box. Okay, so in this week you went through the magnetics part and you saw what was the definition of permeance, and that is something that you use for calculating the inductor values and the transformer values. So basically you went through 3 or 4 steps in transformer design or inductor design. So the first part was, of course, you should know what is the inductor value that you require. So for the power converter, let's say you have a forward converter or any flyback or buck boost converters, you will obviously know what is the L value, L required. So that is calculated from the ripple requirement that is specified in as part of the converter design. So this is something that we have already touched upon in the previous week and the previous weeks, wherein you studied about the non-isolated and isolated DC-DC converters. So this was about the about extraction of the value for L. Now that we have the L value, we need to design the inductor or the transformer, right? So this was the first step. The second step was, of course, you need to know what is the number of turns, okay, for the inductor or in case of transformer for the primary side and the secondary side. And for that, you went through the process of determining what is the area product required so that you may choose an appropriate core based on that, right? So you studied that area product is equal to the product of your window area and the cross-sectional area of your core, right? So that is AW into AC. So based on that, you have the area product, and whatever area product you calculate, based on that, you choose a core which has an area product more than the value that you have calculated. Only then it is physically possible for you to wind the required number of turns on the bobbin of the core. Okay, so yeah, and after that, you also studied how to choose choose an appropriate wire gauge, right? So the selection of the wire gauge is based on the RMS current that you intend to flow through that wire, right? So based on that, you choose an appropriate wire gauge, and you also ensure after you choose the wire gauge that you're able to fix or you're able to wind the required number of turns within the given window area. So you have a criteria for that that says something like KW or KW into capital AW should be greater than N into AW, right? That is, you need to have sufficient area available so that you are able to wind the required number of turns of the selected wire gauge. Okay, so this is something that's a generic process you follow for inductor and transformer design. Okay. Okay, so today we'll just go into the problem solving part of that. Okay, so we will start with this. Which of the following is true? Inductor is an energy storage element. Ideal transformer is an energy storage element. Inductor is an energy transfer device. Transformer is an energy transfer device. So this is, I think, pretty simple problem. You will know that inductor obviously stores energy, correct, in its magnetic field. So this is A is true. Ideal transformer is an energy storage element. No, transformer doesn't store energy. Transformer is an energy transfer device. Okay. So this is something that's a basic for inductor as well as transformer. Inductor stores energy or it's for energy storage, whereas transformer is for power transfer or energy transfer. Okay. This is a very simple question. We'll move on to the next. For a fixed ferrite core inductor, what will be the ratio of storage energy E1 by E2 if peak currents through the inductor are I1 equal to 5 ampere and I2 equal to 10 ampere? Okay, so I1 and I2 are given, and let's say you have two ferrite core inductors or single ferrite core inductor. What will be the ratio of stored energy in both cases? So I1 is 5 and I2 is 10. And let's assume obviously that the inductor is in its linear region of operation of BH curve and the inductor is not saturated. Okay. So what will be the ratio of energy storage in both cases? So again, it is told that it's a fixed ferrite core inductor. Therefore, L is fixed. Correct. So L is fixed. So assuming L is fixed, you of course know the very famous relation between the energy storage and the current that says E is basically half L into I square. Okay. So what you get is basically E being proportional to I square. Correct. So based on this, you obviously get what is the answer. Okay. Yeah. So E1 by E2, as you can understand from this slide, E1 by E2 is going to be what? I1 square by I2 square. Okay. I1 is given as 5, so 5 square, and I2 is given as 10, so 10 square. So 5 square is 25 and 10 square is 100. Therefore, you get the ratio being something like 0.25. Okay. Again, this is a very pretty, it's a pretty simple problem, I guess. The ratio of the stored energy is asked E1 by E2, and you know what is I1 and I2. Therefore, E is proportional to I square, since E is equal to Li half Li square. Okay. Okay. Another theoretical question in front of us. Which of the following are true in case of laminated iron alloy cores compared to ferrite cores? So, A, laminated iron alloy cores exhibit higher saturation flux density and lower core loss. So, this is about what is your BSAT or BM and what about your core loss. Okay. So, what is your BM and what is your core loss? So it's all the options are a combination of both of these. Laminated B or laminated iron alloy cores exhibit lower saturation flux density BSAT and lower core loss. Laminated iron alloy cores exhibit higher saturation flux density and higher core loss. So about the laminated iron core loss. So let me right. So about this, you would know from the lecture slides also that iron alloy cores, right? They have higher saturation flux density. This is an advantage. However, they have a higher core loss. Okay. And this makes laminated iron alloy cores non-employable for high frequency operations because they have a higher core loss. You know that the core loss would increase with increase in frequency. Therefore, you can't use them for high. Thanks for hanging away. There was some problem with the PC, got logged out. Just a second. Okay. So this was about laminated alloy cores. Whereas on the other hand, you obviously know that ferrite cores are used for high frequency applications and they have lower core loss. Okay. And one of the problems with ferrite cores is obviously the opposite, that they exhibit a lower saturation flux density. This is a problem, but the advantage is you have lower core loss. Okay. So again, this is something related to materials. Now we will move on to numerical problems. So most of the problems henceforth are numerical ones. So I would urge you to carefully go through the problems. Okay. Because the problems are a bit tricky. So you need to understand how the problems are solved. Okay. So again, if you have any doubts, you can write in the chat box. I'll check that periodically. Okay. So details of two coils are given. The details of coil 1 and coil 2 are listed below. So coil 1 is a ferrite core. Okay. μr1 is 1500 and the core mean length LM1 is 98 mm. The air gap length is 2 mm and the cross sectional core area is 40 mm square. Number of turns N1 is 100 and the instantaneous current I1 is 5 amperes. And similarly for coil 2, μr2 is 1500, LM2 is 100 mm, AC2 is 40 mm square, N2 is 20 and I2 is 2 amperes. Consider standard value for permeability of free space nu naught. So you know the standard value for permeability of free space is just a second. Yeah. So the permeability for free space, you know, is basically 4 pi into 10 power minus 7 Henry per meter. Okay, 4 pi into 10 power minus 7 Henry per meter. Flux through coil 1 is Phi1 and flux through coil 2 is Phi2. So these are the two coils, right? And the LM1 is the mean length and LG2 is obviously the air gap length. So the question is ratio of flux through coil 1 and coil 2. That is, what is Phi1 by Phi2? Okay, what is Phi1 by Phi2 is the question. So you need to calculate what is the flux in both of these cores and you divide it, you get the answer. Okay, and you realize over here that all the parameters that are given, that is LM is given, LG is given, and AC is given, right? So all of these are geometric parameters. Okay, all geometric parameters are given. And the moment they give N and I, it means that MMF is given, correct? Because obviously your MMF is N into I. So you try to gauge from the question what parameters are given. Okay, so N and I are given. Okay, so since N and I are given, you know that the MMF is given. Okay, you know that. Okay, I think I know logged out. Okay, since MMF is given, you know that since NI is given, you know what is the MMF is given, and obviously since the geometric parameters are also given, you know what is the permeance. Okay. Okay, so if I go to full screen, there is some problem. So I'll just try to continue over here. Okay, so you know what is the MMF that's given and you know what are the geometric parameters. So from the given geometric parameters, you can always find out what is the permeance. Okay. So you know from this what is known as the permeance. Okay. The permeance, or how you denote this, is something like this. So the permeance is given, or if you're comfortable with reluctance, the reluctance is given. Okay. Since you will know what is the permeance and what is the MMF, you know that phi is equal to permeance into MMF. Correct? Phi is basically permeance into MMF. Okay. or correct. So phi is basically permeance into MMF, or you may also write that phi is equal to MMF by reluctance. MMF by reluctance, or 1 by reluctance is permeance, so permeance into MMF. Okay, so you individually need to calculate what is the permeance and multiply that with the MMF, you get what is the answer. Okay. Okay, so first step is simple, that is MMF1, that is N1 into I1. Okay, so N1 is given as 100 and I1 is 5, therefore 100 into 5 becomes 500 ampere meter. That is your MMF1. So you know what is your MMF1, and then you need to know what is your reluctance. Okay, so you try to understand from the given magnetic core, you understand that there are basically two magnetic materials that are in cascade. Okay, therefore your total reluctance would be the reluctance of the first magnetic material, which is your actual core, and you obviously have an air gap over here plus Rg. Okay, so your core reluctance and the air gap reluctance. People generally assume that the core reluctance is very small compared to air gap reluctance, so of course they neglect it. But if you want to get the actual value, what you do is, you know that the reluctance is something like Lm divided by mu naught mu r into AC. Okay, that is L by nu A is your formula, reluctance. So RC is going to be Lm divided by nu naught nu R into AC, that is your cross section, plus RG would be Lg divided by nu R is 1 for air, therefore nu naught into AC, cross section is same. So this is your total reluctance. So 1 by reluctance is actually permeance. So you calculate this value, 1 by this value is your permeance. Okay, from the given diagram itself, you can understand this. Okay, so I'll just take a new slide over here. Yeah, so the point that we were making is MMF is basically N into I. Okay, and reluctance is equal to reluctance of the core plus reluctance of the air gap, which I call it as G. Okay. Right. So you know that RC is basically Lm divided by mu naught mu R AC plus Rg is basically Lg, that is the length of the air gap, divided by mu naught into AC. Nu R is 1 for air. Okay. So this is your total reluctance. Oh my God. There is some problem. Okay. So not into AC. Okay. So this is your total reluctance. From this, you determine that your permeance is basically 1 by reluctance. Okay. Now that you know what is permeance, from this you calculate that phi is equal to MMF into permeance. Okay, or MMF by reluctance. Okay. So this is how you calculate. All the geometric parameters are given, your N and I are given. Okay. So with this knowledge, let's just jump into the problem. That is, MMF1 is 500 ampere meter, and you calculate what is permeance 1 or reluctance 1, whatever is easy for you. And from that, you calculate what is phi. Phi 1 is basically permeance 1 into MMF1. Okay. Then you do the same for the second coil, that is permeance 2. You will know what is permeance 2 and you will know what is MMF2. Therefore, phi 2 is basically permeance 2 into MMF2. Okay. So you take the ratio of both of these, you will get phi 1 by phi 2. Okay. You need not keep this in the form of formulas. Unnecessarily, it would be a bit complicated. You can just substitute then and there, and you find out what is your actual value for. Um, you find out what is your actual value for phi 1, and you find out what's your actual value for phi 2, and just divide it, you will get phi 1 by phi 2. It turns out to be 0.4035. Okay, so I'll just pause over here. Is there any doubt in this problem? Simply we use the fact that phi is equal to MMF by reluctance. Okay, so this is the concept that we apply here. P is equal to MMF by reluctance. Okay, so if you have any doubts, you can write in the chat box, but I guess this is pretty simple. It's just based on the magnetic path, and all the parameters are given in the problem itself. Okay, so you can individually calculate what is permeance 1 or reluctance 1. Okay, and similarly reluctance 2, MMF 2. So phi 1 by phi 2. Okay. 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 So this is a continuation of the above problem. Considering the above mentioned details in question 4 for coil 1 and coil 2, what is the ratio of the instantaneous energy stored, E coil 1 by E coil 2 in the coils? Okay. So again, this is a question on the energy stored. So if you had seen the lecture slides, you would have seen that your so you would have seen that your E coil is equal to, of course, half Li square, half Li square. This is one relation. Okay. Or if you're not able to remember the magnetic terms, you can as well remember the equivalent electrical terms or in the capacitive domain. So you know this is half CV square. Okay. And you also know that energy is basically Q into V. Okay. And you would have transferred your Q. Q is basically your T, right? And if you transfer voltage to magnetic domain, you get MMF. Okay. So basically you understand that E coil 1 by E coil 2 is basically Phi1 MMF1 divided by Phi2 MMF2. Okay. So from the previous problem, you will know what is Phi1, you know what is Phi2, and similarly MMF1 and MMF2, and you substitute that over here, you get what is the ratio. Okay, this is one way of doing it. Or as is given in the problem, you also have, instead of half Li square, you know, E coil can be written as half into permeance into MMF square. Okay, this is another way of writing. Okay, so you know what is your permeance 1, you know what is what is your permeance 2, MMF1 and MMF2, and from that you calculate what is your ratio. Okay, and it turns out to be around 5.04. You will know what is your permeance 1, you know what is permeance 2, and Or similarly, you can adopt this method as well. It is phi1 is known, MMF1 is known, and phi2 is known, and MMF2 is known. Okay. So there is some problem with the. Please do hold on for just a minute. I will just restart the system. It's hanging a lot, so probably that's why it is continuously logging out. Please do hold on for 2 minutes. Sorry for the inconvenience. Hi, thanks for hanging around. So hope now it will be fine. I'll just reshare my screen again. Okay. Okay. Yeah, so we were over here. The ratio of E coil 1 by E coil 2 is E coil is proportional to find MMF. So from that you may find out, or half into permeance into MMF square. And all of these values are known from the previous problem. Okay, so we will move on to the next one. That is question number 6. Design a boost converter for the following specifications. So Vin is 5 volts plus or minus 10%. P0 is 24 watts. V0 is 12 volts, and the switching frequency is 50 kilohertz. Inductor current ripple is 10% of the load current. Calculate the L minimum required to satisfy the above criteria. So you would have known that whenever you design a passive element for any converter, there will be inductor or capacitor, you always design for the worst case. Okay, so it should be considered designed for the worst case ripple. You understand that this is a boost converter, right? So in that case, you try to understand when the inductor current ripple would be maximum. So your delta L is given as 10% of the load current, and your Vin is varying from Vin min to Vin max. And you know that for a boost converter, if you redraw the circuit diagram for a boost converter, you will know that you have the input inductor over here, then you have the active device over here, right? And then you have a diode, and following that you have the load. Okay, so when this switch is turned on for D period, the inductor charges up from V in. Okay, when the switch is on, the inductor charges up with V in. Okay, and when the D is off, you obviously know that the inductor discharges to the load. Okay, so we have to calculate the value for L minimum for the worst case condition. Okay, you would know that if you apply the old second balance in for inductor L, then you would know that since your VL is equal to L di by dt, you can write this during the D period as V in is equal to L into di is delta L divided by dTs. Okay, so what you get is L is equal to V in into D divided by delta IL into Fs, right? This is something that we all know. This is something that we saw in the last week. So in this, you need to make sure that you design your L for the worst case ripple. Okay, and you have V in varying from V in minimum to V in maximum. So you calculate what is your V in into D product, right, for both the extremities, and you consider whatever extremity will give you the maximum value of L. Okay. So we will go through the design steps that we have seen so far. That is, I naught is basically P naught by V naught. Your P naught is 24 watts and V naught is 12 volts. Therefore, it's straightforward 2 amperes. Okay. That is 24 watts by 12 volts. Okay. And the I ripple is given as 10%. Okay. So you obviously know what is your I ripple. But what is of more interest to us is what is the value of D min and D max. Okay, since your V, you know that in a boost converter, V naught by V in is equal to 1 over 1 minus D. Okay, therefore you may write D is equal to 1 plus V in divided by V naught. Okay, so this is the value for D, right, in a boost converter. Okay, so you obviously understand that for maximum value of V in, your D in is also maximum. Okay, that is D max occurs for V in max, and in this case it's computed by 0.625. Okay, similarly you would know that D min would occur for V in min. Okay, so you compute what is your D min and D max. So intuitively or by seeing this also you understand that you should calculate for D max. I'm sorry, you should calculate for D min and your V in should be maximum. Okay, so from this you get what is the value for L. Okay, so this is, I'm not lingering on this for long, but this is something that we have already done for boost converters in week 6 or week 7. Okay, so this is the first part of the problem, that is to calculate the value for L. But the next question is selecting the inductor value of 0.3 millihenry from question 6. We got around 270, 297 microhenries. They have given that the inductor value is 0.3 millihenry. Choose the core that satisfies the inductor design for the given specifications in question 6. Okay, and Kw is 0.6, J is 3 ampere per millimeter square, Bm is 0.2 Tesla. Okay, and they have given 4 options. So we need to choose the core. So if it is given that you need to choose the core, obviously you need to compute what's your area product, and you ensure that Kw and you ensure that you are able to fit the number of turns within the given window area. Okay. Okay. So yeah. Again, so I in max is given by I naught by 1 minus D max, that is 5.33 amperes. So you calculate what is your I value, right? IM. So this is for the computation of IM. Okay. So with the computed, so this is your step number 1. That is, you compute what is your peak current through the inductor. Okay. Peak current. So this is your peak current L. Okay. So the peak current through L is IN plus delta L by 2. Okay. So this is your IM. So once you know what is your IM, you calculate what is your energy. So this is the second step. Okay. That is energy computation. Okay. So you compute what is your energy, and obviously you should compute what is your Kc. Kc is the factor that relates your RMS value with your peak value. Okay. Something that's called the crest factor. Therefore, Kc is basically Im divided by the IRMS, right? So Kc is equal to I max divided by IRMS. Okay. So Imax you computed over here, which is 5.43. And the RMS, we can right now assume that it is inductor carries a constant current, or it's a constant current source. Therefore, IRMS is basically the inductor current average itself. Okay, which is IN. So 5.43 divided by IN is 5.33. Okay. So from that you get what is your Kc.
Sir,
Okay.
what is Kc?
This is 5.333. Okay. So this is your Kc, and finally from that you get the area product. Okay. So this particular relation for area product is something that you need to internalize. That is, area product is given by 2EL divided by Kw into Kc into J into Bm. Okay. Bm, it may be even delta Bm, and that is the exact value that was used in the lecture slides. But you know that for a boost converter, it is always going to be positive current. It wouldn't be negative current. Therefore, you always have a hysteresis loop between 0 to Bm. Okay. So area product is 2EL divided by Kw into Kc into J into delta Bm. Okay. So EL is known, that is half Li square. Okay. EL is half Li square. And what about your Kw? Kw, if you had seen the lecture slides, it is the winding factor, right? Accounting for the wastages that occur in the form of the coil windings, and you have the insulations and the enamel. So all of that result in a poor utilization of the available area. So your winding factor is going to be something like around 0.4 to 0.6. Okay, you can choose any value, any particular number, right? So that is your Kw, and your Kc is known as Kc is basically crest factor, that is Imax by RMS. IRMS is basically your IL average current, whereas Imax is IL average plus delta L by 2. Again, a simple relation, you will know what is Kc. Okay, and J is 3 amperes per millimeter square, and Bm you know. So let me write this up. A separate slide. Okay, so your motive is basically to find out the area product. Okay, so you know that area product is 2EL divided by Kw, Kc Jm into delta B. Okay, so this is your area product. So EL is equal to half L Im square. Okay, so you know what is L, right? And you will know what is your I average. IL average is basically in a boost converter. IL average is I in. Okay, and the relation that relates IL average and I in is I max divided by I average is basically the crest factor. Okay, so this is one, that is Im by average is equal to Kc. Okay, and the next thing that you need to know is Kw is the winding factor that's chosen somewhere between 0.4 to 0.6 for inductors and 0.2 to 0.4 for transformers. Okay, so for inductors you choose between 0.4 to 0.6, and then you will know that the current density is typically chosen to be 3 into 10 power 6 ampere per meter square. 3 into 10 power 6 ampere per meter square. Okay, and for a boost converter, delta B is just Bm. Okay, so you will use all of these values to compute what is your area product. Fine. So you do that and you end up with the area product being 24165 mm per 4. Okay, all other values are given in the question itself. Okay, so the area product is 24165 mm per 4. But so yeah, so Kw is given, J is given, and Bm is also given. Okay, so you need to choose a core that has an area product that is greater than whatever you have calculated. Okay, so choose a core. Choose a core that has AP more than what is calculated. Okay, so yeah, so you know your AP, and from the given data, you will know what is the individual area products for all of the cores. The core data will be given in the question. Okay, here I have not given the exact core data for each of these cores, but generally the area products values will be given in the question itself. So from that, you need to take whatever is the one that has higher, the just higher area product. Okay. Yeah. So here you see that P40 to 29 satisfies our requirement. Okay, it has a higher area product. Okay, but in the given question, they are telling let us choose E40 to 21 9 for question 6. Which of the following options can satisfy the magnetic design requirements? So UR is 1500, U naught is 4.10 to 10 power minus 7 Henry per meter, LG is 1.5 mm, L is 0.3 mm, J is 3 ampere per millimeter square, Kw is 0.6 and Bm is 0.2 Tesla. So this is the next step in the design. That is, we have to choose the wire gauge. SW is 17, 16, 15 and 14. Okay. Okay, so the previous question was about calculating the area product and choosing a proper core for that. Okay, this is the third part, that is the third step that you would generally follow, that is how do you choose the wire gauge. Okay, okay, so for the selected core, the core parameters are also given, that is your AC is 107, AP is 27392 mm power 4, that is your area product, AW is 256 mm square, and your mean length path LM is 108.5. This is also given in the question. Okay, that is the core parameters are all given. Okay, so from this you need to choose you need to choose an appropriate value for the wire gauge. So how do you choose the wire gauge? That is, you have to choose a particular wire gauge AW, and you would have studied that AW is basically IRMS divided by J. Okay, you need to know the RMS value, and you divide it by J, and you need to choose a wire that obviously has a value greater than this particular value. Okay, you need to choose a value that's greater than this value, that is IRMS by J. Okay. So first things first, I would like to draw your attention over here. That is the cross-sectional area of the conductor AW is IRMS by J, right? IRMS or IN, if we assume that is in a boost converter, you know that the inductor is in the input side. Therefore, I am telling IRMS is your IN. Okay, that is IN by J. So IN is known in the boost converter from the given parameters. So from that you calculate what is your AW. Okay, it turns out to be 1.7776 mm square. So this is your AW. Okay, so based on this, you need to choose an SWG that has a higher AW. Not only that, you also need to ensure that, as we have seen in the starting also, you also need to ensure that KW into capital AW, KW into capital KW into capital AW is more than N into AW. Okay. So that means that there is enough area available after you leave the um, allowances due to wastage in the core area. You need to ensure that there is enough area available so that you are able to wind the required number of turns with the selected wire gauge. Okay, so this is something that needs to be always ensured. That is, KW AW should be more than N into AW. Okay, so that is why you also need to compute what is N. Okay, only then you would be able to confirm whether this is true or not. Okay, that is AW being more than N into AW. Okay, so you know what is KW, right? You know what is AW from the data sheet of the selected core, and you just need to find out what is N. Okay, you would know that the relation between the number of turns and inductance is something like N is equal to root over L by permeance. Okay. So N is root, again, this is something that was part of the lecture slides as well. That is N is equal to root over L by permeance. Okay. So you would know what is L, correct? And from the given geometric parameters, you can calculate what is the permeance. Okay. So again, reluctance is something that we know that so reluctance is basically Lm divided by nu naught mu r AC plus Lg divided by nu naught AC. So 1 by reluctance is permeance. So you know what is your permeance, and from that you get what is N. N is equal to root over L by permeance. So you know what is your N. So from that you can check. That is KWAW is turns out to be 153.6 mm square. That needs to be greater than N into AW. Okay. So you do it for all the given options. So of SWG 14, 15, and 16, it seems that it turns out that N into AW would be lesser than your KW into AW only for SWG 16. Okay. It cannot be the other way around. How J differs from I? I don't get this question. How J differs from I means what is the relation between J and I? Is that your question? J is basically okay. So probably there is some bandwidth issue. I will not turn on my camera now. So we will just go to the slides itself and continue here on. A forward converter delivering output voltage of 32 volts with input from battery of 6 volts. So that's a forward converter. You have converter. You have V naught is 32 and input is 6 volts. The operating frequency of the converter is 25 kilohertz and the output load current is 10 ampere, operating at 0.45 duty ratio. Okay. For doubling the output voltage, a 6-volt battery is replaced with a 12-volt battery. So basically your V in has been replaced from 6 volts to 12 volts. The minimum safe switching frequency with which converter needs to be operated is dash kilohertz. Okay. So you would know that your forward converter is something like V naught is equal to N into D into V in. So this N is the control handle that allows you to have a higher V naught than V in. Okay. So since D is given and V in is also given, you would know what is your N. Okay. Okay. So you would know what is your N. But before that, the question is the minimum safe switching frequency with which the converter needs to be operated is dash kilohertz. So this is something familiar with VBF control. You can apply the same concept over here. So for your flux to be maintained same, right? Your flux is maintained same, right? For your flux to be same, it means that your ratio of V and F is same. So V by F is same. So V1 by F1 is equal to V2 by F2. This is something that we do for induction machines as well when we do V by F control. Okay. So the question is simple. Your V is being varied from 6 volts to 12 volts. So what would happen to your F? So or what should be done to your F so that um, the safe switching frequency is maintained? Okay. So for same core flux density, you know that V1 by F1 is equal to V2 by F2. Therefore, F2 would be something like your new voltage, that is your 64 volts, because you want to double your output voltage. So your V naught, or this is your V2, this is your V1. So V2 by V1 is 64 by 32 into 25 kilohertz, that is 50 kilohertz. So you need to double up your frequency so that the relation is maintained. Okay. Yeah. So the question is for doubling the output voltage. The output voltage is doubled. Therefore, V1 is 32, V2 is 64, V2 is 64, F1 is 25 kilohertz. What is F2? So this is again pretty simple. If you want, if you want your converter to operate with your inductor not to get saturated, that is, you would want the flux density to be same or the flux to be same. So phi is same, therefore V by F is also same. Okay. Referring to question number 9, the modified inductance required to maintain the same load current ripple is dash if the inductor in 6 volts input system is L. So what you basically did was, in the question, you change your input. So Vin changed from 6 volts to 12 volts and V naught changed from 32 volts to 64 volts. And obviously we also saw that the frequency changed from 25 kilohertz to 50 kilohertz, correct? To 50 kilohertz. The question is, what should be done to L? So what would happen to L? Okay, if you want to maintain the same load current ripple. So to answer this question, you can go back to the basics. That is, you know that the inductor voltage is going to be L into di by dt. They have given that you want to maintain the same load current ripple. Therefore, di needs to be same, or the delta I needs to be same. Same delta I needs to be maintained. Okay. And you know that what happened to dt? Since your frequency has doubled, dt becomes dt by 2. Why? Because frequency has doubled, f has become 2f. Okay, the f became 2f, therefore dt will become dt by 2. Okay. And what about your inductor voltage? So obviously you know that in a boost converter or in your buck converter also, you know that the voltage across your inductor is basically going to be V in or V naught, correct? So when the switch is on, you know that V in minus V naught is the voltage that appears. And when the switch is off, you know that the voltage is minus V naught. So either way, you know that this V naught has doubled. Okay. So yeah. So you know that the VL is going to be 2 times VL and dt is dt by 2. So we substitute that over there. That is di is equal to VL into dt by L. VL has doubled, dt has halved. Therefore, the total inductor value remains same. Okay. Simple. So this question is done with V is equal to L di by dt only. Okay. You know that the dt will become dt by 2. And the voltage has doubled, therefore V becomes 2V. So from that you calculate what would happen to L if you want to maintain same DI. Okay. Okay, so this concludes the first part of the questions. That is, we have seen, if I have to summarize the questions that we have seen so far, right? I think this is very important for you to, for me to summarize over here. That is, we just saw a few theoretical questions, then we saw a relation between half Li square, correct? And then we went to the particular problem of question 4, wherein we had two coils. They had asked what is phi 1 by phi 2. Okay. The relation that we followed was that phi is equal to MMF by reluctance or MMF into permeance. Okay. And you know what is the reluctance? The formula is given over here. That is, you need to sum up the reluctance of the core path and the sum up the reluctance of the air gap. Okay. So from that you get the reluctance, 1 by reluctance so permeance you apply over here. So this was one question. And the next question was, what is the ratio of the energy stored? So obviously you would know that E is proportional to 5 into MMF. Okay, so you can take the ratio of that, or you know that E is equal to half Li square, or that is equal to half into permeance into MMF square. Okay, that is half into permeance into MMF square. So from that you calculate what is the ratio of E coil 1 over E coil 2. So this was one problem, that is E coil 1 by E coil 2 was asked. One was based on half Li square, the other one was based on half into permeance into mmf square. Okay. The next question was for a boost converter, they just asked you to select an appropriate inductor value, which we did. So considering the worst case, but the next question was that based on that, we had to choose a core. You know the inductor value of 0.3 millihenry. From that, you choose a core from the given options. Okay. So if you have to choose a core, always think about area product. Okay. What is your area product? Okay. You know that the area product is given by 2EL divided by KW into KC into J into delta B. Okay. So KW is given, J is given. Okay. And delta B, you know, is BM, which is also given as 0.2 Tesla. Okay. You know that KC, sorry. So you know that KC is basically your crest factor, which is I max or I peak value divided by I average. Okay. Or I RMS as we call it. So, so from that you get what is your KC. EL is basically half Li square. So from that you calculate the area product. Once you know what is the area product, you will know that you need to choose a core which has a higher area product than this. Okay. So we did the same things over here. That is, we calculated the maximum current, you know, the RMS current. So from that you calculate what is KC and you calculate the energy, and from that you get the area product. So it turns out that you can choose this particular core P4229. The next part of the question was they had selected another core, that is C42219, and all the parameters are given. So the next question is, obviously once you have chosen the core, you should go and choose the wire gauge. Okay. So you can choose the wire gauge. So for that, you know that AW is equal to IRMS by J. Okay. And obviously at the end of choosing the wire gauge, you need to ensure that you have sufficient window area to wind the number of turns. So KW AW should be more than N into small AW. So small AW is obviously the cross-sectional area of your each wire, and AW, capital AW is your window area. That is evident from the selected core. Okay, from the data sheet of the selected core, you get what is the window area. Okay, KW is given. You just need to find out what is N. You need to find out what is AW. Okay, and then you can choose which of these satisfies this criterion. Okay, so yeah, all parameters are given in the problem itself. Okay, so you can find out what is the number of turns. You know that N is equal to root over L by permeance, right? This is the relation. N is equal to root over L over permeance. Okay, so from that you get what is N, that is the number of turns, and you also know the cross-sectional area is IRMS by J. Or in a boost converter, let's assume, if you don't assume the ripple, you obviously know that the RMS current of the inductor is basically your input current, which is again known, right? So this is your AW. You need to choose a wire that has a higher AW, obviously, and also ensure that KW AW should be more than N into AW. So it turns out that for SWG16, this criteria is satisfied. Okay. So this was regarding the boost converter. So we saw three parts of boost converter. That is, one is calculation of the L value. Second is how to choose a core. For that you calculate the area product. And third is how to choose the wire gauge for finding the number of turns. So for that you find out what is the number of turns. That is, N is equal to root over L by permeance. So you find out the number of turns. You find out what is the cross-sectional area AW. That is IRMS by J. And you ensure that KW is more than N into small AW. Okay, so for step one, inductor design. Step two, core selection by calculating the area product. Step three, wire gauge selection by calculating the wire gauge and the number of turns. Okay, and ensuring this condition is satisfied. So number of turns is root over L by permeance. That is a standard relation that you need to just internalize. Okay. And finally, we came to this forward converter. They told that they are doubling the voltage. So how the frequency should change? The question is basically voltage is doubled, output voltage is doubled. How should my frequency vary? So you know that flux is same. So V by F is same. Therefore, V1 by F1 equal to V2 by F2, and that the frequency should also be doubled so that the ratio is maintained. Okay. So frequency is doubled. What happens to the inductor? So you know that V is L di by dt, right? V is doubled, dt is halved because your frequency is doubled. Your dt will be halved. Therefore, L remains as it is. Okay. So I hope till this point the problems are clear. If this is clear, we can go ahead with the next part. Okay. So yeah, okay. So if this is fine, we will go ahead with the next part. Just give me a minute break. I just have some water. Okay, so we'll just move ahead. So again, this is a simple problem. An inductor has to be designed with a given specification. Frequency is 5 kilohertz. Relative permeability of the material you see is 2500. IRMS is 1.5 amps. Number of turns 25. Calculate the achievable flux density in Tesla in the core with given parameters. So flux density is asked. Okay, that is capital B. Okay, so you know that basically B is equal to nu into H, or nu naught nu R into H is your magnetic field intensity, and by Ampere's law you can write that as N into I by Lm. Okay, so The number of turns is known. You know what is the nu R, nu C, right? That is the relative permeability is known, and you know what is nu naught. N is known, I is also known, right? And Lm can be determined from the given dimensions. Okay. Yeah. So L can be determined from the given dimensions. I hope my screen is visible. Yeah.
Yes, sir.
Yeah. So the total is 120 mm, right? And so you consider what should be the path here. Something like this. You can consider the average path. Okay. So you should calculate what is the path LM, right? So the total is 120, correct? So from that, you just need to subtract 10 mm. That would be this path. So that is 110 mm. And similarly, in this side also 150 minus 10, that turns out to be 140. So the total would be 110 into 2 plus 140 into 2. That would be your LM. Okay. From that, you calculate what is B. Correct? Yeah. So as I was telling, B is nu naught nu C into H is Ni by L. And from the given dimensions, you can compute that the total path length is around 500 mm. Okay. So once you know what is the total path length, from that you can get what is your B value. It's a straightforward relation. Okay. So the next question is find the inductance of the coil used in question 10. Okay. So you would know that L is equal to mu naught nu R into N square into AC divided by LM. Okay. Or you also know we also used the relationship previously, that is N square divided by permeance. Okay. Right. So sorry, N square by reluctance. So this is your L. So all the physical parameters are known. You know what is your N. From that you find out what is L. Okay. That is L is equal to N square by reluctance. Right. So reluctance is basically, yeah. So N square by reluctance. So reluctance is L divided by mu naught mu R into AC. Okay, all the physical parameters are given. So from that you find out what is the reluctance, and from that you can find out what is L. So you know what is the L, and you just need to find out the cross-sectional area. So cross-sectional area is as indicated in this figure, right? So this. So the D is given over here, okay? The D is given, and since the D is given, and since you know that the this is around 10
So what
mm.
is D?
Sorry?
So what is
What is?
D?
Yeah, D is
D.
15 mm, right? So that is why your AC is 15 mm into whatever is the thickness over here. You can imagine in 3D that the area of cross section of the core would be the thickness of the core multiplied by whatever is the width over here, right? The 10 mm multiplied by D. That is 10 mm into 15 mm. That would be the cross section of your core. Okay. So from that you get what is AC, right? LM is already known around 500 mm. So from that you can get what is your inductance. L is N square by reluctance. Okay. This relation we used previously, L is equal to N square by reluctance, or you can also write this as permeance into N square. So we used this previously to calculate what is N. N is equal to, we wrote that N is equal to root over L by permeance, right? All these are the same formulae. Okay. Okay. So calculate the RMS value of the input voltage V in, which can be applied for the figure shown in question 10. So what can be the RMS value for the input voltage that can be applied? Okay. So again, so the RMS value, if you want to derive by the natural relation, you would know that V is basically L di by dt, or you may also write this as N into d phi by dt. Okay. So N would remain as it is, and assuming that you are still in the linear region of the BH curve, you can write that d phi is basically 5 phi m, if I can write it, divided by your dt. Dt is basically the time period in a line cycle. Okay, so assuming it's a sine wave, you know that basically the time period is going to be given by what? So this is your frequency of 50 hertz. Therefore, your dt is going to be 20 milliseconds. Okay. So that's going to be your dt, or generically, if it is not 50 hertz, you may write this as 2 pi. This is your radians multiplied by frequency. That is your omega. Okay. So you can substitute that over here, whatever is the dt, right? And from that you get what is your V. Okay, and phi can be further written as B into A, or you may also write this B as nu into H. Okay, into, okay. So instead of that, empirically you would know that for a transformer, the voltage is going to be 4.44 into F into phi into N. Okay, so that is what we are going to use over here. That is 4.44 into F into phi into N. So phi can be written as B into A. Therefore, B is known and A is also known. That is, area of cross section is known from the given question, right? So the RMS value can be computed from this particular relation, that is 4.44 at phi N. Okay, so it turns out to be around 19.6 volts. Okay. Okay, so the next question is, if the required inductance value with the same core size used in question 10 is 20 millihenry, then compute the number of turns to be used for the inductor design. So now they have given what is the number of, what is the L? We need to compute what is the number of turns. We just saw what was the relation between that. That is L is equal to N square by reluctance. Okay. So since your core is same, reluctance will also be same. R is same, right? Because this, it is the same core again, just they are asking you to find the number of turns for a new L value. Okay, L is given as 20 millihenry. 20 milli. Calculate the number of turns. Okay, so number of turns are just going to change. So you know that L is N square by reluctance. Therefore, L1 by L2 is equal to root over N1 by N2. It has a square root relation. Okay, so from that you can just substitute from the previously known value. You can find out what will be the new number of turns. That turns out to be around 47. Okay, because as part of the design, we had already computed what would be the N value, right? That is, it is given in the question, I guess, as N is equal to 25. So N is 25. So, and you also know what is the inductance. So inductance of 0.58905 millihenry is for 25 turns. Question is, with 20 millihenry, what would be the number of turns? So it is just a scaling up, as you can understand. You would get around 47. Okay. Okay. So if this is fine, we will move on to the next question. Which of the following statements is true for both inductor and transformer? During saturation of the magnetic component, they offer very high resistance. No. During saturation of the magnetic component, they offer very high inductance. No. High amount of current will flow due to saturation of the magnetic component. Yes. The reason is in the BH curve, you are somewhere here. So H is proportional to Ni by H is equal to Na by L, or H is proportional to I. So what you would see is that you have already attained BM or your BSAT, but as you increase H, right, as you increase the current, there is no variation in BSAT. Your BSAT is same. So high amount of current will flow due to saturation of the magnetic component, and constant DC voltage applied for longer duration will lead to saturation of the core. Yes. So if you apply constant DC, the inductor would try to keep on storing energy, and at some point it would lose its ability to store energy continuously. Only an air core inductor would be able to do that because its nu naught is very, very small. Okay. Other inductors would obviously reach their BM value soon and it would saturate. Okay. The volt second always needs to be balanced. Okay. Okay. So if this is fine, we will move on to the next problem, next series of problems. Okay. Again, there is a boost converter with input voltage of 20 volts. The duty is given as 0.4 and power is 100 watts. Calculate the value of the inductor used if delta IL is 10% of IL, Fs is 30 kilohertz. Assume a lossless circuit and CCM operation. Okay, so all the parameters are given. The first question is very similar to what we did previously for the boost converter. Calculate what is L. Okay, so from the given, you know that if I have to draw the boost converter again, so this is your boost converter. You know what is your V in here. You know this is your L. So when the switch is turned on, you know that VL is equal to L di over dt, or VL is V in into L into delta IL divided by DTS. So from this you can calculate that L is equal to V in into D divided by delta IL into Fs. So V in is known, D is known, delta IL is also known, and frequency is known. You get what is L, right? So yeah, so you know what is the average value of inductor current. That turns out to be around 5 amperes. The power is given, correct? 100 watts, assuming it's lossless. You divide the power by the input voltage, you get the input current or the average inductor current, right? So this is your I in, okay, and delta IL would be 10% of that. That is the ripple they have given. So delta IL is 0.5 amperes. So from that you get what is your L. Okay. So the first part is very similar to what we saw previously. Second question, based on question 16, select a suitable core for the inductor based on the table below. Consider the inductor to be a single winding inductor made of ferrite core. Approximate average value for the inductor current to be same as RMS value for simplified analysis. Just a second, I just. The circuit like boost has to be remembered. So I will tell you a simple way. Don't study the boost converter something like this. Okay, it's always going to be difficult. What I suggest is for any converter, buck boost or buck boost converter, you understand that they are all based on a half bridge. So half bridge means there are two devices, something like this. I am drawing with proper MOSFETs, but once you get the hang of it, you can just draw generic switches. Okay, so all of the circuits are based on this half bridge. Okay, so you have the half bridge. So this is what is known as a switching node. Okay, so this is called a switching node. Okay, this is your switching node. So the idea is, let's say you have a DC voltage over here. Okay. So, and let me call this as S1 and this is S2. So V in you have, and this is S1 and S2. Okay. So what happens, right? What happens is when S1 is on, okay, when S1 is on, you can understand that, let me call this as VA, switching node is VA with respect to a common ground. Okay. When S1 is on, you understand that, where did it go, man? When S1 is on, VA is equal to V in. And conversely, when S2 is on, when S2 is on, S1 is obviously off, complementary switching. So VA is equal to 0. So S1 and S2 are becoming on, off continuously. So what you would eventually get for VA would be something like V in 0, V in 0, V in 0. That is why I'm calling this a switching node. So it is continuously switching between VA and 0, VA and 0. Okay. So this is the voltage that you have got over here. Okay. Basically, you have chopped the voltage. After this, what I do is I will put one LC filter. Okay. I will put one LC filter. Right. So, and let's say you're feeding a load out of this. So obviously this load would be drawing I naught current. Okay. And capacitor being, if you assume the capacitor is in steady state, it can only draw the ripple current. So it would only draw delta I current. It cannot draw a constant average current, because if it draws a constant average current, capacitor voltage would go on increasing. Right? In steady state, capacitor would draw only the ripple current. So the total current is something like I naught plus delta IL. Okay. Right? So what you have done is you have got a switching voltage over here. Using this inductive and capacitive filter, you have got a constant V naught at the output. Basically, I have converted this into this. Okay. And what happened to the ripple part of voltage? The ripple part of voltage is appearing across the inductor. Okay. The ripple part of voltage is appearing across the inductor. Okay. So this is basically your buck converter. Okay, this is another way of drawing the same buck converter, right? So I will take the all as an line. So as a switching node, from that you put something like this. So this is buck. Okay, and let's draw the same half bridge. So this is called a half bridge. I have drawn the same half bridge once again. Okay. Try Okay, so this is your buck converter. Okay, this is basically your diode. Okay, and for boost converter, I was just mentioning that you have something like um, okay. So again, draw the same half bridge. Okay, and this is your inductor. Okay. Okay, so you look at both of these diagrams. Akshit, is my screen visible? Yeah. So you look at both of these diagrams. So what is the only difference? For buck converter, Vn is in the input side, L is in the output side. And for boost converter, what we did was basically we transferred L to the input side, okay, and rearrange the circuit something like this. It's like a complementary of the buck converter. You look from the input side. So what you do is you transfer the Vn to the output, and you transfer the capacitor bank to this side, okay, and you get a boost converter. You look from this side, it's like a boost, right? That is, if you look from this side, this is a boost converter. Buck converter will look like a boost converter if you look from the output side. Okay. So isn't it easy to remember? Just remember a half bridge, and from that you get what is your buck and boost. Is it fine, Akshit? Anyway, so I'll just move ahead. We are a little bit short. Okay, so select a suitable core for the inductor based on the table below. Consider the inductor to be a single winding inductor made of ferrite core. Approximate average value of the inductor current to be same as RMS value for simplified analysis. So all the code details are given over here. Okay, so as we saw in the earlier problem, first was to find out the inductor value. Second is to find suitable core. So core means your mind should go towards the area product. And you know that area product is given by something like 2EL divided by KW KC into J into BM. Okay. So the values for all of these would most likely be given in the problem itself. Okay. So, yeah. So KW is given in the problem 0.6. If they have not given also, KW is anywhere between 0.4 to 0.6, and BM is generally 0.25 Tesla. Okay, that is something that was mentioned in the lecture slides also. For inductor, it's 0.25 Tesla, and for transformer, it's 0.2 Tesla. Maximum you can go till 0.3 Tesla, and J is 3 ampere per millimeter square. So with this information, you can compute what is your area product. Okay, 2EL divided by KW KC J into BM. So EL is half Li square. Okay, so L is something that is known from the previous problem. We just computed what is L, 0.53 millihenry. Okay, so half into L into I square. Okay, so I is something that you calculate, correct? That is for the given boost converter. You will know what is your I minimum, your I average, and your I maximum. From that, you compute what is EL. Okay, so that is your area product. So now that you have got area product, from that, from the computed area product, you need to select a core with an area product greater than this value. Okay. Therefore, from the given options, you will see that you need to have about 31,000 mm power 4. Therefore, what satisfies us only this P42/49. It has area product more than 31,000. Okay. So third question, you can obviously guess that it would be relating the wire gauge. Okay, so the next question is calculate the air gap length required in the core selected in question 17 if the required permeance is 5.2302 into 10 power minus 7 Henry per turn square, and relative permeability is 2 tons. So UR is given, and relative permeance is also given. Okay, what is the air gap length? So you know that the reluctance is RC plus RG, right? That is Lm by nu naught nu R AC plus Lg divided by nu naught AC, right? So this is your reluctance. 1 by reluctance is equal to permeance. So permeance is given, right? So permeance is given. You just need to find out what is your Lg, correct? So this is something that can be determined from this particular relation. Okay. Yeah. So the same relation is being used, and you get what is your value of Lg. Okay. This is not question 2, it's question 16. Okay. So you can get what is your Lg and calculate the number of turns to be wound for the inductor based on question 16, 17, and 18. So what is the number of turns? So again, the same relation that N is equal to root over L by permeance. The reason is that L is equal to N square by reluctance or N square by permeance. So from that you understand that N is equal to root over L by permeance, right? That will give you the number of turns. So it turns out to be around 32. Okay. And the last question is find out the wire gauge size. So 3 wire gauge sizes are, anyway, it's highlighted in red, but anyway, 3 wire gauge sizes are given. So what do you do for finding out the wire gauge size? You compute what is your AW and ensure that KW, AW is larger than N into small AW. Okay. So how do you find out AW in the first place? AW is basically IRMS over J. Okay. In this case, IRMS or the average inductor current is basically IN because it's a boost converter. So IN over J. So we compute what is AW, that is IN over J, 1.67 mm square. Okay. So you need to ensure that AW, KW should be more than N into AW. So yeah, AW, KW is 108.6 mm square. So you can see that SWG14 is the correct value. Okay, again, there is a problem, boost converter problem, wherein what were the aspects of this question? Find out what is L. Okay, find out what is L. Second product is choose, select the core. Select the core as in like find out the area product. You know, area product is basically 2EL divided by KW, KC, J into delta B. That is your area product. And third question is, or third major question is SWG selection. Select a wire gauge. So you need to know what is your AW, small AW. And ensure that KW should be more than N into small AW. Okay, so these are 3 major parts. With a single question, within a single question, you get all of these 3, right? And other than that, you also saw other. You saw that AW is basically IRMS by J. Okay, and you also know that L is equal to N square by reluctance or N square into permeance. And you know the reluctance is basically RC plus RG. That is Lm divided by nu naught nu RAC plus Lg air gap length divided by nu naught into AC. Okay. So, and 1 by reluctance is equal to permeance. So these are the major formulae that we applied so far for this question. Okay. Yeah. So just to conclude the last 10 problems once again, right? That is, yeah, that is in this problem, the core was given. You just needed to find out the flux density, right, in Tesla. So B is equal to nu H or nu naught nu R into H is NI by L by Ampere's law. So all of these values are given and you compute what is the mean magnetic path length from the given core. You get what is B. Okay, B is equal to nu H. The next question is find the inductance. Inductance is again n square by reluctance or n square into permeance. Okay, so and reluctance is a physical or geometrical parameter and you can of course compute it from the given parameters using this particular formula. Okay, or not this particular formula, also the reluctance formula that we just wrote previously. Okay, so from that you get what is your inductance. And finally, what is the RMS value? V is simply 4.44 into F into 5 into N. There is something that's applicable even for induction machines or power transformers. Okay, 4.44 at 5 N. This was one problem. The next problem was what is the number of turns required? Again, it relies on L is equal to N square by reluctance or N square into permeance, right? So this was one problem, okay, where L has a square root dependence with the number of turns, and then we considered the boost converter problem, right? In that boost converter, we needed to compute what is the value of L. That was the problem number one. Second problem is how to find out the core. For that, you need to compute what is your area product AP, correct? And you ensure you choose a core that has a greater area product. And next question is find out the air gap length. Again, from the reluctance equation, you find out what is the air gap length. Okay. And number of turns, again, L is equal to N square by permeance, N square by reluctance, or N square into permeance. And finally, you end up with what is this standard wire gauge size. So AW, or the cross section of your wire, should be I in by J or IRMS by J. Correct. For boost converter, IRMS is I in. If it was buck converter, it would have become I naught for buck converter. So you need to consider the current as suitable. Okay, for boost converter, it is I in. For buck converter, the inductor is in the output side, it is I naught. For buck boost, it is somewhere in the middle, so you have I naught by D, right? So it would obviously vary, or sorry, I in by D. Okay. So, and you also ensure that KW should be more than N into AW, right? So with that, you choose what is the appropriate value for the wire gauge. Okay. So this concludes the problems. I think we have seen around 20 problems today. So if there are any doubts, you may go ahead and ask now, or else we can conclude the session for the day. Right. Sorry, it is SWG, sir, means? Yeah, so there are two air gauges, SWG and AWG. Okay, so you can, based on the problem, you can see like each of the SWG is a separate convention standard wire gauge, or AWG is American wire gauge. So both of these are standard conventions. Okay, so AWG 14 may have a particular area for wire conductor. It's just a convention. Based on the given data only, you can choose what SWG or AWG is required. Okay. Okay, so if there are no doubts, we can close for the day, Akshit. Thanks for attending. Yeah, and have a great week ahead. Okay. I will stop sharing. Yeah. Okay. Bye. Good night.